Welcome to BAMA. I'll start by telling about our next talk. It's going to be on October 18th. We have the dynamic duo of Gary Gordon and Liz McMahon from Lafayette University telling us about the card game Sept. They have a wonderful book from Princeton about that topic. But tonight, I'm delighted to present to you my colleague, Sara Krehbiel. Sara Krehbiel joined the SCU faculty in 2019 after teaching for 4 years at the University of Richmond. After growing up near Stanford University, Professor Krehbiel completed her bachelor's degree there and went on to earn graduate degrees at the University of Texas, Austin, and Georgia Tech. Her areas of expertise include differential privacy and graph theory. It's on that latter topic that she'll talk to us tonight. So I'd like to just mention some Zoom etiquette. I'd like to ask you to keep yourself muted unless you want to speak up. And the way we're running this tonight is that you may unmute if you have a question, or you may put a question into the chat. Either way is fine. So now, please welcome Professor Sara Krehbiel to tell us all the ways to color a graph. Welcome.
Hi, thank you everyone for coming to the talk. Frank gave a lot of my bio info already, but I'm going to just go through and do a little bit of that as well. So I'm a professor here in the Department of Math and Computer Science at Santa Clara. I'm going to talk to you about one of my multiple research projects that are going on. I like this one because it is the most colorful of all of my research projects. And I have a weekly meeting on my schedule that is called coloring. And I just like the idea of having an hour of coloring a week. It's not necessarily coloring in that sense, but so before I get started with the technical stuff, I also just wanted to add on, I'm going to have some questions for you throughout the talk. So feel free to unmute if you have a question. Also, please unmute if you have an answer to a question that I have. So I wanted to tell you just a little bit about how I became a computer science professor. I like to talk about this because even though the process of going to college, getting a PhD, becoming a professor, that involves a lot of hard work that nobody else can do for you, it's really not a solitary process. And I think that the community that you luck into and the community that you build for yourself is really important. So here are some kind of childhood photos that show just a little bit about what growing up was like for me. I was really lucky to be born to two parents who valued education really highly in the Bay Area. This in the upper left is me as like maybe a 2-day-old wearing a Stanford baby onesie. And that's my dad. He's a Stanford professor. He's in political science. My mom is retired now, but she's a speech pathologist who spent most of her career working in the Palo Alto school district. So that was always obviously important to them, and that made it easy for it to become important to me. Did a lot of reading growing up, a lot of reading and napping, sometimes at the same time. I was very, very lucky that it happened to be that the person who was born into my family after me ended up being my best friend. My sister and I are very close. We're actually kind of tangentially coworkers now too. So not with a Santa Clara, there's a Santa Clara connection. She went here for her undergrad. She's a full-time employee at Meta, which is what we're supposed to call it now, but Facebook is what most of us think of it as. And I've been doing some part-time work there also in one of my other areas of research and data privacy. I had an awesome group of girlfriends growing up. A lot of kind of consistency across the years was really helpful for me. So this is a photo of 3 of my best friends at our 5th grade graduation, then us recreating that photo later at our high school graduation. It was really great for me to have role models that were in my peer group. All of these lovely women are in STEM fields. So Lisa over here is a stem cell biologist at Harvard. Lainey is a civil engineer and she manages big construction projects. And Heather is a soil scientist who was working at a lab at UC Berkeley for a long time. I actually recently saw her at her baby's 1-year birthday party. So it's great to be in touch with all of them still. I'll go through this quickly because Frank actually kind of already said all the places that I went to school, but I had kind of a circuitous geographic path to and from the Bay Area. So I went to college in my hometown at Stanford. Then I finally left the Bay Area to do a master's at UC Austin or at UT Austin. And I also like to tell people that even though I had all of these great influences growing up, I still had a little bit of that kind of outsider feeling that a lot of women have in computer science. I actually didn't take my required computer science classes until junior year of college, so I had never programmed before then. And so I decided to do a master's kind of as a stepping stone, make sure I really liked it, even though I really did kind of like it right away. I went to Atlanta and got my PhD at Georgia Tech. Then I spent 4 years at Richmond. Loved it there, but was really missing the Bay Area and family. So I'm excited to be back. And now I've made a bunch of new great colleagues here. So now we can kind of move to the meat of the talk. I'm going to be talking about a particular type of reconfiguration system, but I wanted to sort of seed the talk with our activities that we were working with, which were some other reconfiguration systems. So if you were coming later on, we were working with the ricochet robot system. That's not, to my knowledge, a super well mathematically studied object, although maybe it could be. That could be future work. The 15 puzzle, where we have tiles that we slide around and try to get the tiles in order. This is a good example of a reconfiguration system, which in general consists of a problem and a set of solutions to the problem. So we would think of the solution to the 15 puzzle as being the tiles all in order. But we're going to think, for the sake of reconfiguration systems, being less goal-oriented. Wherever you are, like, that's a solution to the problem. So all of those intermediate states we're going to call solutions. We also have a way of transitioning between these states or these solutions. So there's a modification rule. And in the case of the tile sliding puzzle, the rule for modification is you can slide any adjacent tile into the open cell. So what the object of study that we're going to be focusing on is something called a reconfiguration graph. That gives us a way to organize the set of the solutions and to look at its structure. So here I have two solutions. Can you see my cursor, by the way? Great. So I have two solutions, and these two are going to be adjacent, so connected by an edge in the graph, because they differ only with a single modification. So if I slide the 7 over, I get this solution. You can also convince yourself that if your empty cell is on an edge, there are 3 different tiles that can slide into it. So I'm going to have 3 lines leaving this state going to different states. Whereas if my empty tile is in the middle, I have 4 lines indicating that there are 4 different places I could transition to. So that's just kind of reconfiguration systems in general. Today, we're specifically going to talk about a graph coloring reconfiguration system. A bit later on, I'm going to tell you about how this serves as a mathematical model for studying some more practical problems like scheduling if you have a bunch of constraints. But before we can really start talking about those applications, we have to understand the thing we're studying. And so that's going to involve building up some background. So I'm guessing that I actually know some of you are like graph theory specialists. So I know that at least some of you have seen some graph theory before. And I want this to be accessible for people who've never seen graphs before. So if at any point you have clarifying questions, I'm going too fast, please just slow me down. We might end up with a lot more to get through than we have time for, and that's fine. I want you to walk away with understanding some of the basics instead of seeing a bunch of slides that you didn't make any sense of. So a graph is just it's just 2 things. It's a set of things called vertices. Sometimes we call those nodes, and it's a set of things called edges. So before we kind of start drawing pictures, and pictures are going to be where we really start to understand, we can think of a really technical specification of a graph. And so the way I read this set of equations or this set of symbols is I can see that this graph has 3 vertices, and I'm going to give them letters. So I'm going to have something called V, something called W, something called Z. Now an edge is a pair of vertices, and I imagine it as being a way that connects these 2 vertices. It makes them neighbors. So this isn't very elucidating like this. What I want is a diagram that illustrates it. And now this starts to feel like something that you could actually start to make sense of. So here I have 3 vertices, and the vertices are represented by these filled in circles. I have labels written here so we can kind of keep track of them and talk about them. And so V, Z, and W are connected by 2 edges. The first one, VZ, that gets me from V to Z, and the second one, WZ, gets me from Z to W or back again. Now we can talk about directed graphs, and directed graphs, each of these edges have arrows. So maybe there's a to and a from place. But for this talk, we're just going to be talking about undirected edges. So going from W to Z is possible if and only if going from Z to W is possible. So this graph is a particular type of graph called a path. It's a path on 3 vertices. And you can think of the word path just the way you think of it in English. You can walk around starting from V, you can get to Z, then from Z, you can get to W. You can visit all of them. So there's another special type of graph that's good to have kind of more vocabulary in our pocket called a cycle. And from a path, we can create a cycle just by adding 1 extra edge. So here I have a path on 4 vertices. I'm going to use the notation P subscript 4 just to say path on 4 vertices. It's always going to look like this. Now, maybe it's not always going to look like that because I can move where the nodes are, but the definition of a graph doesn't care where actually the nodes are. It just cares how the nodes are connected by edges. So I have my path on 4 vertices that has 3 edges connecting 4 vertices. I add a 4th edge and I get a cycle. And then I can think about this just 1 step further. I can think about graphs on 5 vertices. A path on 5 vertices looks like this, and then a cycle has 1 extra edge. Okay, so I'm going to pause if you have any questions. And if you don't have any questions, then you can think about my question, which is, in general, if I'm working with n just being a placeholder for the number of vertices that I have or number of nodes that I have, can anybody tell me how many edges I should have in a path on n vertices and how many edges I should have in a cycle on n vertices? Okay, so I have one answer that if we're working with a path, there are n minus 1, and I like that answer, but I know that my next animation is going to give the answer to the cycle. Can anybody tell me the second answer? How many edges do I have with the cycle? N, perfect. Okay, so path on n vertices has n minus 1 edges, and a cycle on n vertices has n edges. Another type of graph that's a good thing to have in mind is something called a complete graph. So the word complete indicates that we have the complete set of all possible edges are all present. So if I have 2 vertices, then there's only 1 edge that's possible because there's only 1 pair of 2 things. If I have 3 vertices, it turns out that the complete graph on 3 vertices is also the cycle on 3 vertices because there aren't any edges besides these edges that are necessary to take a tour around the graph. Now, that's not true for the complete graph on 4 vertices because the cycle we've seen on 4 vertices has 4 edges, but then we're missing these edges that turn the opposing corners of our square into neighbors. So sometimes it's helpful not just to think about positive examples of things, but negative examples of things. So here's an example of a graph that isn't complete. This graph isn't complete because I have a 5th node up here that doesn't have any edges connecting to the other vertices. So I would need an extra 4 edges connecting the 5th node to all the other vertices to make this a complete graph. So there's kind of a pattern here. If you are trying to count up all of the edges on complete graphs, you might be able to come up with a general formula for the number of edges that are in the complete graph on n vertices. And I think that one easy way to do this, or one starting point for doing this, is to think about how many extra edges I get going from K2 to K3, how many more going from K3 to K4, and so on. That's not the only way to think about it, though. This is not a super obvious question. So what I have in this final graph is I have K4, so the complete graph on 4 with one extra node. So I have all the edges of K4, but then how many extra edges do I need to make K5? Can anybody just shout that out? So Frank was showing 4 fingers. If I connect this to 4 extras. So what I'm doing is I'm adding up all of the numbers starting from 1, then I add 2 more, then I add 3 more, and then I'm going to add 4 more. And Jauhen also put in a formula here, which is exactly correct, although that's actually not a formula that I have up here. But if you're familiar with choose numbers, you're going to know that that's the right formula here. So if you want to think about marginally how many extra edges we have, we start with 1 for n equals 2, and then we add 2 extra for n equals 3, then 3 extra, and so on. When you get to n equals 5, the last thing that you're adding is these 4 extra edges. And it turns out that if you sum up all of these things, you get Jauhen's formula, which is n times n minus 1 over 2. And that also happens to be n choose 2. So if you're familiar with choose numbers, this is the idea of I have n things, and I want all of the possible ways to choose 2 of them, which makes a lot of sense if we're thinking about edges, because I have n vertices, and all of the possible edges are all of the choices of 2 of those vertices. So any questions about this from anybody before we move on? If you're not into this type of counting, that's okay. It's not great for my research project in general, but it's totally okay for this talk. Okay, so what's missing from the examples so far? This is an easy non-technical question. The last example looked like this. This was sort of my teaser photo. What's the difference? Here's a hint. The title of the talk. I haven't dealt with colors yet. So what we want to talk about next is graph coloring. So graph coloring, like graphs, also has a technical definition, which we can write down using symbolic notation, but it doesn't start to really feel like it's getting under your skin until we draw pictures. But here's a technical definition. So I'm going to start with a natural number. So that's anything 0, 1, 2, 3. And I say that a K coloring is an assignment of a number in the set between 1 and K to each vertex of G. So I've said the word color here, but I'm not using any colors yet. So let's start thinking about numbers as colors. So if we have K equals 2 colors, we have this set 1 and 2, and let's imagine them as colors. So just like every time you see a 1, think of that as being red. Every time you see a 2, think of that as being blue. So let's come up with a particular example. We have to have a graph in order to color it. So this is a symbolic description of a graph, but this is the graph, the complete graph on 3 vertices. So I have all 3 edges are present. Now I like to think of this assignment C. So this is just a function, but instead of thinking of it as a function, I like to think of it as paint by number instructions. So my function could say C assigns the vertex V the color 1, it assigns the vertex W the color 1, and it assigns the vertex Z color 2. But then I get to draw this graph like this with these colors. Okay, so that's a coloring in general, but usually when we talk about colorings, we're talking about a specific type of coloring that has an extra property associated with it. We say that a coloring is proper if the color we assign V is different than the color we assign W, if V and W are adjacent in the graph. So neighboring vertices that have an edge between them, aren't allowed to share colors in a proper coloring. Okay, so this is a pretty straightforward question. Can somebody tell me, and if you're willing to unmute yourself, can somebody just shout out which of these colorings is proper and which is not?
Is the second one proper?
Yeah, the second one is proper. And the second one is proper because each of these vertices have a different color. So in general, you don't need each of the vertices to have a different color, but because this graph is complete, all of the vertices are neighbors with all the other vertices, so they all need to have different colors. Here, we're violating this edge constraint by assigning these two colors, these two vertices the same color. It's not the case that the color assigned V is different from the color assigned W. So we have the left is not proper, the right is proper. Okay, so now that we have the idea of proper colorings under our belt, now we can talk about this application. And I want to give my, my standard caveat that I think applications are super important for a lot of reasons. But I also think that mathematics can be beautiful by itself. And so in the case of graph coloring, I think that the applications are useful, but I think that the problem is nice just for the sake of the problem. And I like the structure of the problem, and I like puzzles just for puzzles. But here's a scenario where we actually can think about graph coloring as having a tangible meaning. So imagine that a school has a bunch of sports teams, and we want to schedule a practice time for each of those sports teams. But it's the case that some people are playing multiple sports. So for example, if Brian, is playing soccer and hockey, we can't schedule soccer and hockey to have practice at the same time. So these are kind of our rosters for our simple little sport setup. Now, with the rosters, we can build a graph that represents the constraints for the scheduling problem. So I'm going to have a node or a vertex for each of the sports. And then if the sports have a person in common on the roster, I'm going to draw an edge between them. And that edge is my way of saying soccer and hockey are not allowed to be scheduled at the same time, because then Brian couldn't attend both of them. Hockey and badminton can't be scheduled at the same time because Dante and Elaine wouldn't be able to attend both of them. But if I look at the soccer roster and the badminton roster, there's no overlap. So that's not a constraint. So it's okay if those are scheduled at the same time. So here are two colorings. Actually, these aren't our two colorings from before. Here are two more colorings. And now that we have an application, we're not only going to associate a number with a color, we're going to associate a number with a potential time that I could schedule these. So one, for example, might be I'm scheduling an afternoon practice, and two might be that I'm scheduling a morning practice. So one of these is a problem and one of them isn't. Anybody want to let me know which is which? The second one is the good schedule, yes. So the second one is the good schedule because if I think about what's wrong with the first schedule, I have hockey and badminton are both being scheduled for the morning, but Dante and Elaine were both on the badminton team. You don't need to remember their names. You just need to see that there's an edge here saying that there's somebody in common. So if instead we take badminton and we move it into the afternoon, then that's going to be good for everyone. So the way we think about coloring and schedules is an improper coloring is a bad schedule, a proper coloring is a good schedule. Okay, so once we have the idea of proper colorings in mind, we can start to think about, well, how many colors do we actually need in order to get a proper coloring? So if I have a bunch of teams and I have a bunch of overlaps between the rosters, this question says, how many different time slots am I going to need in order to schedule all of these teams in a good way? So this is given by this symbol, this chi symbol, which is called the chromatic number. So I take a graph and I say that the chromatic number of a graph is the smallest value of k, so the smallest number of colors for which there is a proper coloring. So here's some examples, and I'm not going to make you answer all of them if you don't want to, but I would love it if somebody could at least answer the first question. So now how do I unwind this question? What I'm saying is, what's the chromatic number of the complete graph on n vertices? So if I have n vertices and they're all adjacent to each other, then how many colors am I going to need to color the vertices so that none of the adjacent vertices have the same color? And I don't know if this is a new answer, but somebody said N. So whether that was an answer to a previous question or this question, it's the right answer. So if I have the 4 vertices, for example, they're all going to have different colors because they're all connected to each other. Now, if I have a path, I'm going to kind of go through this one quickly. I'm going to say that no matter how many nodes I have, I'm going to be able to color this path with 2 colors because I can always just alternate and I don't have to worry about things going anywhere else. Each node is going to have a color that's different from its 2 neighbors, and I'm going to be able to get everything for no matter how big n is. This question is a little bit more subtle, and I'm going to give you a minute to think about it. If I'm thinking about a cycle instead, so think about a loop where I'm walking through all of the nodes, how many colors do you think I'm going to need to color that cycle? There are kind of 2 right answers and 1 very good answer. Okay, I have a 3 question mark, an n-1, and a 3. So if n is sufficiently large, then definitely I'm going to say that n-1 is enough. I'm also going to say no matter what n is, well, n has to be at least 3 because we don't really have, the idea of a cycle doesn't make sense for less than 3. But 3 is going to be enough. And here's how I can show you that it's enough. I can think about just coloring the path. And then that last vertex in the path, let me go ahead and give it its own color. I really only need to do this though. Oh, this is a great, clever suggestion over here from Phoebe. I only need to do this if my cycle is odd. So if instead of having 5 vertices connected in a cycle, I had 4 vertices connected in a cycle, then I could just alternate. I could go red, blue, red, blue, and then that would go back to red. There would be no constraints if I don't have this X in the middle. But if I have an odd length path, then the color that if I'm starting from red, blue, I want to make this red now, but then this red would connect to another red. So I'm going to need an extra 3. Okay, so I want to move away from colorings for just a second to talk about another property of a graph that is going to be relevant to colorings pretty soon. So we have the idea of a chromatic number, and that has to do with how many colors we need in order to properly color a graph. But now put colors aside for a second. I'm going to define a maximum degree of a graph to be the largest number of neighbors that any particular vertex has. So we can color a complete graph on n vertices with n different colors. But if I'm a complete graph on n vertices, if I'm one of those nodes, how many neighbors do I have? I suspect with the timing of before, I'm going to get an answer in the chat pretty soon. Feel free to unmute. Okay, I'll save you. Oh, good. Thank you, Tom. So if I have n vertices, then I'm neighbors with everyone else. So that's n-1. So each of these 4 vertices have 3 edges leaving it. So the degree of every vertex is 3, and that means that the maximum degree is 3. So a path can be colored with 2 vertices. Now the maximum degree of a path is also 2. The maximum degree of the path is not the degree of every vertex. A path has 2 vertices called leaves. So a leaf in a graph is a vertex that only has 1 neighbor. So the first and the last vertex on this path are leaves, but every other vertex has a neighbor to the left and a neighbor to the right. In a cycle, it depends on the parity of the number of vertices, whether I'm going to need 2 or 3 colors. But if you just visually think about a cycle, you can convince yourself that all of those vertices have exactly 2 neighbors. So the max degree of a cycle is 2. Okay, so now we have all of the machinery that we need to understand not the proof, but the statement of a powerful graph theory result, which is Brooks' theorem. So Brooks' theorem says if I have a connected graph, and haven't defined connected, but what you have in mind is probably correct. It's a graph where all of the vertices are reachable from all of the other vertices. So if I have a connected graph, there are two special cases. Either that graph is an odd cycle, or if the graph is an odd cycle, or if it is a complete graph, then the number of colors that I need to color that graph is exactly one more than the max degree of the graph. So here are these two special examples. If I have the complete graph, that max degree is n-1, and I need one more of those colors in order to color the graph. If I have an odd cycle, the max degree is 2, and I need 3 colors to color the graph. Otherwise, all I need is delta colors, and I will be able to color the graph. So, whoops, this is a bad coloring. I meant to flip two of these reds and blues. So if I alternate these reds and blues, that would be a good coloring. So if I have for example, an even cycle, then the max degree is going to be 2, and 2 is enough to properly color the graph. I could also just take an arbitrary graph. So here's an example of a graph that isn't a cycle or a complete graph or a path. If I look at each of these vertices, I can see that this one that I'm hovering over here has degree 3, and that's the most number of neighbors any vertex has. But I can also see that I was able to color this graph using only 2 colors. So that's where this inequality comes into play. So exactly 3 colors is enough, but I might be able to get away with less than that. So any questions about Brooks' theorem? Okay, so we're finally now ready to start talking about this as a reconfiguration problem, the way the sliding tile puzzle was a reconfiguration problem. So this is kind of motivated by the question, if I have a K that's big enough, so if the number of colors that I have is at least the number of colors that I need, then I know I have at least one proper coloring of a graph. So what's a good way of organizing all of the ways to properly K-color a graph? So I'm going to define a specific reconfiguration system, and this reconfiguration system is associated with a reconfiguration graph that I'm now going to call the K-coloring graph of G. So I get a graph, and I get some number of colors, and I say that the K-coloring graph of G has states and it has transitions. So the nodes of the graph, the states of the graph, that's all of the ways to K-color the graph. And then the way to transition between K-colorings is by taking a single vertex and recoloring it. So again, this makes a lot more sense with a specific example. So let's take the complete graph on 2 vertices, which is also a path on 2 vertices. So if I zoom into each of these little boxes, that's the base graph that I'm working with. But I'm giving myself 3 colors. So the 3 coloring graph of this 2-path, or this complete graph on 2 vertices, ends up looking like a 6 cycle. And I've organized it in this kind of wonky way for a reason that I'm not going to spend too much time going through. But if I can kind of pay attention and see how these transitions make sense with what I've described as being single vertex recoloring. So if I have green then red, I can opt to recolor red as blue, or I can opt to recolor green as blue. So no matter where I am, I'm using 2 colors, and I'm able to take my free color. And so in this case, my free color is green, and I can either recolor the left green or I can recolor the right green. So this is a way that we can reason about the coloring graph, which is an organization of all of the ways to properly K-color a graph. Let me pause here for just a little bit and see if there are any questions about this, because this really is the fundamental object that we're working with.
If you switch 2 of the colors, like all iterations of the 2 colors on the board, is that 2 different ways to color the graph?
So you're saying, for example, if I
switch all the reds with all the blues?
Yeah, no, that's a great insight. And actually, what you're talking about is you're talking about there being underlying symmetries of this graph. So if I take all of the reds and replace them with blues, and I take all of the blues and replace them with reds, then I would get a copy of this graph that looks exactly like this. I just have different colors. And so what that means is that you can see a bunch of kind of rotational symmetry in all of the coloring graphs. So let's just go back to an example of this graph, for example. So this graph at the bottom, it's not a very symmetric graph. Every vertex is sort of playing its own role in this graph. But here, I somehow don't really care about the differences between each of these colors because it turns out they're all isomorphic to each other. And what I mean by isomorphic is if I just relabel what it means to be green and what it means to be red, then this vertex can become this vertex. So that's a really great insight. Okay, so here's some additional examples of coloring graphs. And these are actually going to be like pretty straightforward examples because I'm going to start with a really easy base graph. So my base graph here is just a single vertex. So this is K1 because it's complete. It's also called I1 because it's one isolated vertex. So if I pick K equal to 1, so if I only have one color, then there's one way to recolor, or there's one way to color a single vertex. Now, if I pick K equal to 2, then there are two ways to color that vertex. And so these two ways to color the vertex are two nodes in C2 of I1. These nodes are adjacent because recoloring a single vertex gets me between one and the other. So think in your head for a second about what C3 of I1 is going to look like. And if you were thinking it would look like a triangle, you're absolutely right, because it doesn't matter what color I pick, I can always just recolor to a different color. And now if you have the pattern for C3, you probably have the pattern for C4. If I have 4 colors, then I can swap between any of those 2 colors to color that single vertex. So one pattern here is that I1 has K coloring. So C1 of I1 has 1 coloring, C2 of I1 has 2 colorings, and so on. If I'm looking at the organization of those colorings as a graph, what does this graph look like? What type of graph? Is it a path? Seeing a shaking head, not quite a path. See, universal graph, that's very close. I like the word universal. So I think complete graph is what we're going for. And somebody else said KN. So KN is exactly right. Except that we don't have an N defined here. So what we're actually talking about with what we actually mean by N, usually we're thinking the number of nodes. And here the number of nodes is actually defined by however many colors we have. So we have the complete graph on K nodes, on K vertices, where we have 1 vertex per color. And you can see that going back to Ian's sort of observation, all of these complete graphs all have a nice symmetry associated with them because all coloring graphs have nice symmetries. Okay. So here, this was sort of like a teaser question. I was setting this up as though this is going to be a question with a nice simple answer, and it doesn't have a nice simple answer. So if I consider the path on 3 vertices and 3 colors, it turns out that there are 12 different ways to color these 3 vertices using 3 colors. The orientation of these has a very nice symmetry associated with it. I sort of have these 3 squares that are all connected by edges. And I can also think about, let's go back to Ian's observation. If I flip the roles of, let's say, red and green, for example, you can stare at this and see that what we get is that this graph sort of just like rotates left to right, sort of like flips on itself, which is pretty nice. And you can flip any 2 and that'll do different types of flips, or you can flip all 3 and that'll do like a rotation. It's pretty cool. Okay, so this graph is colorable with 3 colors, but this is a path. So remember that a path is actually colorable with 2 colors. Can anybody tell me, this is not a trick question. Oh, I see something, a triangle of squares. I like that. Can anybody tell me if we reduce the number of colors that we have, so we only have 2 colors to work with now? I guess the full answer to the question is, what does the 2 coloring graph look like? But maybe a stepping stone question is, how many different ways are there to color a path on 3 vertices if I have 2 colors? Two. Sharon got the right answer. So I have 2 different ways. So if I just have red and blue, I can go red, blue, red, or I can go blue, red, blue. I can't really alter anything else because that would be violating one of the constraints. Now, these are the nodes in my coloring graph, but then I also have to think about the edges in my coloring graph. So there's only one possible edge, but drawing an edge between these 2 nodes would mean that they differ on a single color. And they don't differ on a single color, they differ on 3 colors. So let's kind of go back to this example and make sure that we understand the structure of this. So if I take this coloring, for example, which lives up here in the 3 coloring graph, I have multiple options for what I can do because I have a free color. So I can use green either to color the right node or just the left node or just the middle node. And so that's kind of what this structure looks like. If I'm starting without having a free color, so I don't have a color that is unused, but I have 2 leaves that have flexibility associated with them. So this green leaf has the flexibility of turning red, and this red leaf has the flexibility of turning green. So I have different constraints at different places in this graph. So it's not a complete graph anymore where every vertex looks the same, but it is a graph with lots of symmetry where all of the 2 colorings of the graph sort of look the same in the context of the structure of the graph. So all of the 2 colorings have 3 neighbors associated with them, and all of the colorings that use 3 colors have 2 neighbors associated with them. So another thing that we see from this observation is it's not necessarily true that all coloring graphs are connected. So I used the word connected before, and now I'm finally going to define it for you. We say that a graph is connected if there's at least one path between any pair of vertices. So here I can't get from this leftmost vertex to this bottom vertex, so that's not connected. But here, this example I used before, pick any 2 vertices. So maybe I pick this top one and this bottom left. Now they're not adjacent to each other, but I can take a path that goes through a vertex and I get there. So for coloring graphs, if we say that the coloring graph is connected, that's when we call the graph mixing. So I can have a graph like the path on 3 vertices that is mixing for some value of k. So for example, if I have 3 colors, then my 3 path, I can get from any 3 coloring to any other 3 coloring. But if I only have 2 colorings, that's not 2 mixing. So recall we had this nice theorem by Brooks that said, how many colors do I need in order to have a proper K coloring? So there was a specific sort of statement that if I had 2 special types of graphs, then I needed delta plus 1. But in general, if I have at least delta plus 1, that's enough. So delta plus 1 ensures that I have a proper K coloring. It turns out that delta plus 2 ensures that the coloring graph itself is connected. So if I have just 1 extra color, that's a guarantee that I'm going to be able to get among all colorings. Okay, so let's kind of bring this back to like a little bit of reality for a second. This is going to be a bit circuitous, but I'm going to pose the question, why do we care whether a graph is K-mixing? So why do we care whether all of the colorings can be reached by single vertex recolorings? So the answer is kind of multi-step. I'm going to start with a general statement, which is that generating random numbers is computationally useful. So this is kind of coming out of nowhere, but hopefully you believe me. And even if it's just because you like to play games on the computer, Generating random numbers allows a computer to simulate rolling dice. So you can like play a fair game the way rolling dice would be a fair game, or maybe shuffling cards if you're playing a card game. So here's where we kind of stretch the analogy just a little bit. But let's say that our athletes have scheduling preferences. So in our example, we had a morning practice and we had an afternoon practice. I actually played ice hockey for a year in high school. And I have to tell you that it was not my preference to get up at 5 a.m. to go use the university's ice skating rink to practice ice hockey. So it might be the case that I like some good schedules more than I like other good schedules. And now maybe the person in charge of scheduling is really nervous about being told that they're coming up with an unfair schedule that's prioritizing some people's preferences over others. So if that person wants to remain unbiased, then what they're going to want to be able to do is they're going to want to be able to have some way of picking a proper K coloring of a graph so that each coloring is equally likely. So that would be a certificate of them saying, I was just rolling the dice and picking a random coloring that worked. I wasn't taking anybody's preferences into consideration. We were only obeying the strict constraints. So there's a general procedure that we can do. And how are we doing on timing, Frank? Like 10 more minutes?
Sure, that's just fine.
Okay. So there's a general procedure that we can take. And the basic idea is that we're going to start at an arbitrary coloring. So I'm not going to call this random because there might be a bias. So maybe the coloring that I'm starting with is the coloring where I don't have to wake up early to go to ice hockey practice. But what I want to do then is I want to be able to visit all of the neighbors in the coloring graph. So I'm going to take my arbitrary coloring and one by one, just make changes to the scheduling of one team and then make changes to the scheduling of another team and so on. So it's mathematically true that after you explore enough, after you make enough of these random changes, you are equally likely to be anywhere in the coloring graph. So that is a perfectly fair coloring, but that's only true if the graph is connected. If the graph isn't connected, then making these little changes isn't going to get you from one disconnected piece in the graph to another disconnected piece in the graph. So now I just want to gesture a little bit of our kind of active research areas. There are two problems with this random walk strategy, and I kind of already alluded to one of them. It requires that the graph is mixing. So if the coloring graph is disconnected, it's like, well, can't do anything. Now, it's not actually true that you can't do anything. It's just that you can't take a purely random walk approach. There's another like pretty interesting technical thing, which is that even if the graph is mixing, I said that if you explore long enough, you will get to a uniformly random color. But there are some graphs where you get kind of a bottleneck where the graph isn't disconnected, but there's a big cluster somewhere in just one tiny little way over to get over to another big cluster. And if that's the case, then it's going to take a very long time for this procedure to eventually reach a uniform distribution. So we can kind of think of this as like a bottleneck. So what we want to be able to do is use our knowledge of the structure of the coloring graph, which is just taking all of the observations along the lines of stuff that we've talked about in this talk so far, and figure out whether we really are totally out of luck if the coloring graph is disconnected, or maybe we can use Ian's observation about the symmetries of the coloring graph to be able to jump from one component to another component using the knowledge that those components all kind of look the same. We can also sometimes use structural knowledge. We want to be able to use structural knowledge to sometimes overcome these rapid mixing bottlenecks, and sometimes symmetry is going to be an option there too. So just in the last couple minutes, I want to show you a little bit about this visualization software that several students helped us build. So our issue, before we were interested in sampling, we were interested in a structural property called cut colorings, which I'm not going to go through and explain right now. And the problem that we ran into is that graphs that exhibited this structural property called cut colorings we're like kind of small as base graphs, but you can see from the stats here, and you can also see from this diagram here on the top right, they're very large as coloring graphs. So I gave you a bunch of diagrams of actual coloring graphs. If we want to use a complicated coloring graph at all, it gets really big really fast. So this one has 864. There are 864 different ways to four-color this graph. So I'm going to see if I can switch over now. And this is kind of like the mystery portion, because this web version of this software, and this is actually open source software. Let me go back for just a second and show you down here. So Alok Satha, he was a really, really awesome undergraduate student a few years ago, super into a bunch of different substantial programming projects, both just purely out of his own interest and doing research with various people. He has an awesome GitHub that includes all of the software for this. So this is all open source software. So you can actually get the software that works really well, or you can get the slightly buggy version that I'm going to use for demonstration purposes here. So what I can see here is I have in the upper left, I have our original example of a graph on 3 vertices. And then over here, it automatically generates the coloring graph for me. So this is where the bug sometimes happens, but we'll see sometimes if you click on one of these vertices, you get an error. Okay, I don't think we're going to be able to, this isn't going to work out for this demo, but sometimes if you get the good software, clicking on one of these vertices will show you the color that's associated with it. So here I'm using 3 colors. So what that actually means is that I'm in one of the vertices that have 2 neighbors as opposed to 3 neighbors. Where it gets useful is if I want to explore, and you can see sort of the shifting around, there's some really nice physics functionality here. So if I want to explore a bigger graph, then maybe looking at this graph just looks like a mess. But looking at sort of the symmetric structure of the graph is easier to do with some graph algorithms and some visualization software. I'm going to see whether I'm going to be able to regenerate this. Yeah, so regenerating shows how stuff kind of like moves around until it can, and that way things can kind of spread out nicely. So the other thing that you can do over here, the way that I got these is with this GUI that allows you to add edges between nodes. And then you can also get rid of edges. And so we're going to roll the dice and see whether this graph, if it decides to generate, it's a pretty cool looking graph. So here I have one vertex that is connected to, let me make sure it's 6 other vertices. I'm going to only give 3 colors and click generate. So now I can see this blob, and it looks kind of like a more structured blob. And if the randomness of physics works out nicely, it's going to nicely separate. And so what I can see here is this is a case where I really have like 3 blobs that are just connected by a single vertex. And this is actually an example of where the sampling algorithm isn't going to work very well, because whichever of these blobs you start in, you're going to bounce around in that blob for a long time before you ever randomly are able to go to another blob. And if you're sort of following the structure of why this coloring graphs looks like it does, let me turn off physics here. It turns out, if you're familiar with the concept of a bipartite graph, that this is a bipartite graph. And so I can actually think of that as generalizing this guy, which is a bipartite graph. And so it's recoloring these vertices that get us these squares. And over here, recoloring these vertices get us these 6-dimensional squares that are living in these blobs over here. So let me just kind of quickly recap, just so you can remind yourself of all of the cool things that you learned. We talked about a graph being a set of vertices and edges. We talked about what a proper coloring is. It's an assignment of colors to vertices that don't disobey any of the constraints. We talked about how this problem can model problems like scheduling in the real world. We learned a mathematical theorem called Brooks's theorem that tells you how many colors are necessary in order to properly color different types of graphs. We talked about how coloring graphs are these kind of meta graphs that can organize all of the proper colorings of a graph. And we talked a little bit about this nice visualization tool. And I want to say that in general, visualization tools can be very helpful in building intuition about structural properties of things that are too complicated to be working through every single thing by hand. We talked a bit about what random walks are and how that can be used to yield a random coloring. So that's a sampling algorithm. And then we also talked about how understanding those conditions under which the random walks are useful for sampling is an active area of research. So I want to be able to let you guys ask some questions. But first I want to thank you. And I also want to thank the many people that are listed here. So one of the fun things about this project is it's pretty easy for people to jump into and get involved. So I've worked with several professors, including recently one of them here at Santa Clara, and a bunch of undergraduates, both when I was at Richmond and since I've been here at Santa Clara. So please feel free to ask any questions, and thank you so much for coming.
Thank you, Sarah. That was just splendid. And I think I hear the sound of thunderous applause with my super ears that extend across our entire audience. But I bet people do have questions. I'd like to invite people to go ahead and unmute yourselves if you'd like to ask something. Seeing a little applause icons here, a little loved it in the chat. So on behalf of all those expressing those things, I want to thank you for a splendid talk. So let's allow people to ask questions if they wish. Well, I was really impressed by the complexity of the coloring graph when the graph itself got only a little bit larger than your examples that you showed us. So what will break your visualization software?
What will break it?
Yeah.
That's a good question. I'm actually not sure what the threshold is, but I think it's pretty simple, and it counts up all of the colorings, and beyond maybe 1,000. It actually, let's see if I can do a really quick, simple experiment. I'm just going to add a bunch of nodes. Actually, the best way is to not connect them to anything. So I get this pop-up that says that the coloring graph is not loaded due to size, but then you can choose to display it anyway. So if I choose to display it, then it says, well, that's an error. And it actually kind of breaks things a lot. It doesn't tell me the size, but if I, it is telling me that, so what's going on in the left is this is the block cut tree associated with the coloring graph, for those of you familiar with like what a block or a cut of a graph is. And so it is giving me the information, at least, that this is a bi-connected graph. So it'll give you like some information, but it won't always like provide the entire graph.
And I think there was a question in the chat to provide references. Or
yeah.
So wants to learn more.
That's a great question. So that's something I should have kind of like in my pocket. What a good starter for this is. Honestly, like a great starter for everything graph theory, I think, is Wikipedia. I think that they have really excellent descriptions of different graph concepts. If you just Google graph coloring, and if you Google graph coloring reconfiguration systems, you can find a number of papers that study this type of thing, including a couple of mine. So yeah, I think probably Google is your best bet, but in the future, I'll try to have a curated list of some good primers.
If G has chromatic
Sarah,
number lowercase g. Oh, sorry, there was a question in the chat. Go ahead.
Sarah, I have a question. So you started out with that little 15 tile guy.
Yeah.
And you said that you can have a connection if you can any way you can move a tile. Do you ever consider only moving the tiles in such a way that you're sliding a bigger number, next below the smaller number, and see what happens in that case?
Yeah. So, I mean, with lots of these reconfiguration systems, you can toy with the actual modification rule. And so what you're basically doing is you're saying, actually, I'm going to get rid of some of these edges by saying that there are only certain types of edges that are allowed. And it sounds like I would have to think about the tile a little bit more, but you might even be talking about kind of like a directed reconfiguration system, like if you can move one way, but you can't move back the same way. Somebody was mentioning this when we were talking about the robots as well. So like, can I move backwards from the place that I ended up at and get at the start place? So the robot reconfiguration system is not going to have those kind of two directional transition rules for that way. But yeah, so a lot of the broader literature on reconfiguration systems kind of explores when little modifications like dramatically change the problem versus changing it just slightly.
And Sarah, did you see a question from Shamil in the chat?
Yeah, so Shamil's question is, if we have chromatic number G, then can we say that G is G plus 1 mixing? These are the questions that have like easy answers, but I always get tangled up because actually what I did not talk about is I did not talk about a graph property called degeneracy. And so there are relationships between the chromatic number and degeneracy that yield that chromatic number bound. And so I think that the answer to that question depends on the gap between chromatic number and degeneracy. It would be an easy thing to figure out in like 5 minutes offline, but I'm not going to be able to figure it out right now. Can colorings count the configurations of a 15 puzzle? Oh, that's a good question. So I think that these puzzles are these reconfiguration systems are too different that you can't really embed one in the other. That's not something I'm certain about, but my guess is that they're probably too different of reconfiguration systems. There are examples of reconfiguration systems that seem like totally different problems, but end up being the same problem. I don't think that this is an example of that.
If there are no more questions, I'm going to stop the recording, but let's all show our appreciation again. Thank you so much, Sarah.
Thank you for coming, everyone.